I also start this lecture by talking about my own background, especially when I talk to students who I like to talk a lot about, and they oftentimes ask me the question is, how did you get where you are? Or, where did you come from? And I have to say, it's been a journey that I never knew I'd end up here, if you asked me when I was young, right? So each time it just kind of grew, and suddenly I end up here as an architect working in the area that Max described. But basically, out of high school, I went into college. I thought of sciences, probably like any good Asian, I guess. And I was also good at the arts. I went to college thinking that, of course, I wanted to be a visual arts major, but my father said absolutely not. So then I chose to go into biology. What I did was every year that I was in school, I always took a studio art class, and I never told him. So back then, we didn't have things like minors and stuff like that, and so I just went ahead and took whatever class was available because I did not have first choice to get into them because I was not a major. And at the end, they offered me a scholarship to go to graduate school, and I thought, wow, okay, maybe I'm actually okay at this. I decided to change gears, and I went into architecture school instead of medicine. So when I got to architecture school, I didn't know a lot about architecture. I just thought, okay, well, this is kind of cool, and it's close enough to arts and sciences that maybe it'll be okay. But I started to ask questions because I thought that was what school was about, right? To challenge the norms, challenge the things that were out there, and to really push the limits so that when we get out there, we can think about the future. And so when I was in graduate school, I started thinking about how architecture could be an extension of the human body, that this inanimate material that we see around here can actually be part of our body, be sensitive like our bodies, and actually be something that we can feel through. Because if you think about it, our clothing can already do that. When someone's pulling on your shirt, you can actually feel what's going on. You can feel heat coming through when someone's standing a little too close. All these types of things we can feel with our clothes, which is inanimate. The question to me is like, why can't we do that with architecture? So I started to look at prosthetic devices. You can see here the Rebecca Horn project on the right with the fingers. You can imagine that the more you use it, the better you get at it. Not only dexterity that were part of the body. Again, I differentiated art from architecture in the fact that architecture is something you could touch. No one's ever going to say, do not touch architecture, right? But art was always like, oh, step away, stay back, don't touch it. And there's a certain amount of frustration here in the case of a face actually moving in to build a lock, right? And I won't go into the details of this. And at the same time, tried to look at how to animate things, right? So that somehow it had a way to embody what humans are, right? In this one, it actually, when you clicked a lever, the eyelids actually would open and close, right? And start to imitate movement in different ways. And then I came upon Merleau-Ponty, right? And the phenomenology of perception, which is much about how we can experience through a lot of these things that, the intellect is not as important as the experience itself, because we can intuitively feel and sense things through our bodies. So the biggest example that I think was really key in his book was about this blind person's cane, right? And so a blind person, the more they use it, they actually can feel the ground, right? They can feel texture, they can feel depth, they can feel a lot of things through this inanimate object. So then to me, it's like, okay, if that could be the case, then again, why can't architecture be like this? Something that we use and hold on one side and feel on the other. You look at high performance things like this runner, right, with the blade. There's a lot of controversy separate to this runner, but what happened ultimately is that the runners that had feet and legs felt that Pistorius had an unfair advantage by having this inanimate thing, right, attached to his leg. And so by saying this, it's basically saying it can be better and it can be higher performing even than the body. And then outside of the body, many of you probably drive cars, right? And you know that space. You know the space in your bubble space when someone's standing a little too close. But even with another layer. You have your clothes, and in this case, a car, and then outside of your car, you can actually feel and sense how much space you have around it. So then again, to me, it's like, well, why can't we do that about architecture? How come I don't know how much space is beyond these walls? And instead, we actually are living in these boxes, right? So we have these human bodies, these shapes that are really hard to define, generally the same, but very, very unique. But everybody has to sit inside a box, and the box is very, very different than how we behave. So it was about 2008 that I saw this video sit, the spoilers start to come up. It starts to perform relative to the speed. And changes through all those things, as well as the interior. As you sit in it, it starts to hug your body, and so that whoever sits in it starts to conform to that kind of customization. And so I thought again, it's like, okay, if cars can do this, why can't architecture do this, right? And so I started with this kind of premise, this ultimate thesis that's, again, when in school was really important to me, and to this very day is something that I still strive for. I can't say I haven't found the answers, but you can kind of see how that education and that time of questioning and challenge starts to drive an entire career in searching for those things. So I became an architect after that. I practiced for about 17 years as a licensed architect in a typical architecture firm before I decided to move away from it. I was very frustrated because as climate change was happening, and I was consumed with climate change right before 2000, like in 1999, I just couldn't sleep even, because I couldn't understand why in architecture no one seemed to care that climate change was happening. Nothing was happening at that time. Now you hear a lot about it, but you start reading about it, you start seeing cars and vehicles start to change, energy systems, but architecture basically is the same. And if you look around it to this very day, it basically is still the same, right? So I started to look at architecture and start to move into research. I decided to go, and it's like, well, if nobody's going to be making these products for architecture, then I will try, right? Why not? And I get into a field that, to be honest, is very, very sparse with design and very sparse with products for climate change, for environmental changes, and all these things. And it's still sparse. But the idea that I have is, okay, in a facade system, why can't it at least start, like this video, to change so that you can see it responding to the outside in some ways, to the outside environment? Why can't we design something in what we call is to optimize it? So in architecture, the problem is we design things for the worst case scenario. The structure and the ceiling, the walls, the thicknesses, it's all made for really hot or cold temperatures. It's either made for super strong, loads, all just in case that there's a hurricane that's really big, all in case that there's, temperatures that drop that. But it costs a lot of money to do so. So why not optimize it? Why not design it so that it just adjusts automatically and becomes flexible, so that it just performs how it should when it's time to do that? So there are different things that are out there you can see here on trying to make that real customization happen. This is actually a very cool project. I didn't design this, but by a project called by Studio Ini. The problem that you see here is, look at these wires, right? There's thousands of wires. There's a lot of Arduino happening. Ultimately, let's face it, there's a lot of problems that are going to happen. It's going to fail somewhere, sometime, right? And it's not going to be performing at its best. So I was very wary of looking for things that needed wiring, that depended on computation systems to operate, right? It needs all these sensors. It needs a hell of a lot of stuff to operate. And like I said before, I came really consumed with this problem with climate change, right? Although Elizabeth Colbert came out with this book in 2006, she was writing these essays that I was reading that led to this book in the year 2000, right? I want to go back and talk a little bit about architecture. I don't know if any of you know a lot about architecture, but I'm going to give you the fast, very quick history of thermal comfort for architecture. Before, in the early or late 1800s, early 1900s, we didn't have a lot of electricity. We didn't have a lot of these things or air conditioning to cool the buildings. Instead, we had very thick walls and very small windows. And what that did was it insulated the outside from the inside, kept the interior cool during the summers, kept it warm during the winters, and the windows were small so that that thermal temperature would not transfer very easily, right? But then quickly moving forward, a lot of technology came about, plate glass, long-spanning steel, and what we get was a big problem with temperature. Everyone thinks, oh, look how close I am to nature, I can just sit here and open the window, but the reality is very hot inside. You get solar radiation coming in, you cannot cool these spaces, and we have big problems. Moving a lot forward, right? Everybody loves the windows, the view, I'm so close to nature. But the problem over time is now we have elevators, we have taller buildings, and we have the intent to make efficient mechanical systems. The way we make efficient systems is by having double, triple glazed windows, but also windows that can't operate. So the reality is what we're living in here are things called capsules. They have these clear glass that one might think actually is clear, not really clear because you see how dark they are from the outside, you can't see in. But the inability to actually even breathe the air outside, right? Because all temperature controlled, it's all filtered air, it's all coming in artificially. So again, going back to the idea, I started looking, it's like, well, why can't buildings be, like animals? And why can't the skin of a building be like human skin? The human skin can do so many things, but we do very little with our building skins. All we have is like clear, you can see through it, you can insulate it, make it thick, you can make it pretty, and it's very simple. And instead, all these years, in the past, I don't know, maybe 30 years, all the money has been going into making efficient mechanical systems. So whatever you put on the outside, as long as we can pump the air conditioning through, then we're all good, right? But then we have this energy crisis and energy issue. I'm going to talk a little bit more about that energy problem later. So one of the things I started looking at, given that introduction and all these facets, coming in and influencing how I was thinking, I started to look at smart materials. And just to let you know, smart materials is different than the word smart used in other terms like smartphones, etc. It actually is a material that requires zero energy, no controls to operate, no computer controls. And it's something that responds automatically to the environment, period. That's a smart material. It's very different than a smartphone that requires all of that plus more, and what we think smart is, right? So here is the smart material that I work with. It's a thermal bimetal. It's a lamination of two metals together. It has different coefficients of expansion, basically. Basically, all materials expand when heated, but if you put two materials together that one side expands more than the other, it'll curl. And so you can see here in this metal, as the temperature goes up, it curls, and as it goes down, it flattens again. It just does it automatically. It does it millions and millions of times, and it's molecularly bonded. So what I'm going to do now is I'm going to show you different projects that I've worked on using this material for, again, a lot of the purposes for some attitude towards environmental sustainability, is for equity and trying to use it in places that we don't have electricity or not access to electricity, that is an inexpensive product. And finally also for wellness. So there's a lot of intent into what I design that's for people, for product use, and developing them ultimately for architecture. Keep in mind that in architecture, everything that you see here is a product too, right? Everything from the grid that you see, the tiles in the ceiling, the concrete on the floor, the drywall, on the walls, this is all products. So this is the world that I live in, is trying to look at those products and try to rethink those products for architecture. In this case, you see here the thermal bimetal. This is one of the first projects that I worked on. We tried to combine it with computation models so that the design, from the beginning, actually can go all the way to fabrication, that we can use just a single model to do that. And it was very difficult at that time in 2009. It seems very easy today, but we didn't have those models. This is before Grasshopper. This is when we actually had to use CATIA to do it, and it was extremely heavy. It took us almost 24 hours to instantiate this model. I don't know if some of you are computer savvy people, but to actually get our model, to get all the information in it, to even, render, took 24 hours to run it. It doesn't seem like that long ago, but it was not easy. The idea that we had here is to get rid of any fasteners, because again, I'm in architecture. There's a lot of fabrication issues relative to skilled labor, unskilled labor, construction, trying to find a way that you can eliminate the use of tools and try to eliminate a lot of structure too. So here's the tab, slot and tab connection that we were able to put this entire thing together in probably less than 6 hours. You can see the surface was a ventilating surface, like it said before. When it's cold, it's flat, and the idea is that when it gets hot, it would crimp and allow air to pass through the surface, right? Again, originally I was trying to think of how can we open up a surface without having a window? Do we have to have a window to let air in? And can we do this through walls? All kinds of geometries also start to play a role in what I do and trying to open up surfaces and close them. You can see here is a simple aperture that by heat, it'll open and also close. Then we take those things and change the geometry so that we can multiply them over a surface. In this one, if you look really closely, and I keep having to remind myself to try to find this piece, it's actually made out of a single geometry. So a single piece, when rotated and put together into this field, will start to define the entire surface and make some of these openings in strategic places. So, you know, when I was an architect, everyone always said, it's like, oh, you must be really good at math to be an architect. It's actually not true, and every architect laughs. It's like, well, whatever. It wasn't until I started doing this kind of work that all of a sudden it was like, wow, I had to really go back to some high school math, right? Everything from geometry to trigonometry to, you know what I mean, formulas and things like that, which I never used in my entire career until I started doing this. Started doing all kinds of other things too, and here you can see, it was a project for Toyota where they wanted this traveling project that could just be thrown in a box and assembled in a few hours at a different site. We used theater lights for this one. And you can see what happens is we made this loaf, is what we call it, so that the light was hot enough to drill a hole. You can see how the pieces then start to bend. So interested in designing a thing for Toyota as much as using it as a vehicle to do research. So for me in this project, I decided it's like, okay, I'm going to make these things, but I want to see how much further I can make, you know what I mean, these arms actually rotate. I want them to get out of the way, because if you can imagine in a cantilever situation where it's stiff, all it can do is curl, but it can't get out of the way. But if we pivot it, all of a sudden the whole thing can actually move out of the way. And so this was a big deal for us. You can see here, even when we reconfigured it and took all those, you know what I mean, stacked pieces and reconfigured into this tower, a portion of it you can see in the sun actually started to rotate. So that to us is also important as an architect, because we want it to respond to the sun. I was not as thrilled to make it respond to theater lights, but you know, again, that's where some of our funding comes indirectly. The same idea then we applied to this project for Louis Vuitton. And then finally, in the evening, it'll be fully rotated so that you can actually see the LED screen behind it. So there's advertisements and things going on. We are also doing energy generating now, which is kind of funny because we didn't set out to generate energy. We just started to build these things because we wanted to solve a few problems again. We look at these things and it's like, well, you know, here's the common ventilator you see everywhere. It's great, it works great, it's simple, but the problem is you can see when it does get cool at night, cold air actually will go into these cracks and actually down, and they don't close, they don't shut, it is just always open in warehouses. So then we tried to make these things rotate with heat. So the heat, the combination of the framework, we can actually make them work together so that they open up, they can spin with the heat, and when they cool down again, they start to shut and prevent that cold air from going in. By doing this, in this case, it's a combination of wind energy that can make these things happen, but we also do it with solar energy. So in this case, it's a solar turbine that we make. This is just one of many of them. You can see that it'll just perpetually go just by using this bimetal. The idea, again, originally came from the fact that we wanted to make these bus shelters for people who are sitting there for a long time in the heat, so that they would not only be shading structures above, but they would actually provide breeze, one-to-one, that we did not need electricity in remote areas, that there was nothing for someone to actually steal, like a solar panel, that somehow these places were actually cooling instead of, dehydrating to many people. You can see here, we go through I could talk about every single type of wheel that we've made. There are different kinds, there's different variations. We do a lot of prototyping. I just show these things to you all too, because things that we show in the end, some of them seem crude, some of them seem very developed, some of them seem simple, but there's a lot behind it to make it happen. In this one, for example, too, this was a really exciting moment for us, because we were able to make this one thing, instead of go this way and go back again, right? So it's a one-way system. This system actually can somersault. Can get this thing to operate in the correct way. When you're using pivoting systems, suddenly you're also working with this mass, right, on one side of the pivot, or the weight on another, and trying to figure out how to really make these things happen. And so these have now come into our world as a really important component that we never thought we'd need before. That pivot that we developed before, a lot of times we'll do these things and we don't know where the applications are, led to this project in Washington, arrogant about it, but I just don't have the time to do that, whereas I'm much more interested in trying to progress the research itself. But these guys were really convincing to me. They gave me a story. It was during COVID when we were in lockdown, and they called me up, and I said, I don't do these installations, but they said that, they're so upset, sad, because like everybody, they weren't able to go to their graduation, and so there's no way that they can commemorate their graduation. And during this time, it was so difficult that as a very tight-knit group of boys, how can they do it even remotely? So, it kind of made me sad, and I was emotional at that time, and so I was like, okay, let's try to do something. So I used this kind of lever arm that you saw. All 73 boys, we made these 73 spheres of glass, positioned them in such a way so that these lever arms, the back of the lever would actually hit the sphere next to it, so that in effect, each of these spheres was dependent on the entire group to actually make some noise. And so in the end, it's a piece that actually, when the sun goes across, you'd have this kind of sounds or music actually playing, so that the entire group was together, right, as a cohesive group. Sun shading, this is actually a big thing for us too. Again, I get a lot of inspiration from my biology days in college. I never did it intentionally. I just do it probably because I like it. And it's combined with the computational tools out there. The fact that, so this project was done quite a while ago now, in 2011. I told you before we were using CATIA before this. We started to use Grasshopper in 2011. We ended up with this project helping Grasshopper develop their platform, so that it's available today for everyone else to be able to go again from design all the way to fabrication. I can do a full lecture on that, but I won't do that now. The idea for this project was to do two things, was to actually provide shade below and to also ventilate the space. So if it gets hot, we can try to find a way to use the environment to do that. And a lot of that was from solar radiation. We connected the model so that, again, here we have about 14,000 pieces that were all unique on this project. You can see on the right, in the top gray area, they would be able to thin out in areas that we didn't need strength or structure. And then the bottom in the gray area, they had longer tails in the area that we needed coverage for solar radiation, or we didn't. And you can actually see that in a slide that's coming up. We connected that to other programs like Ecotech is what we have. In this one, the red basically tells us where the surface is being hit by the sun most times of the day, most times of the year. And the areas in blue are in the shade at all times. So this kind of told us that's like, well, we don't need the blue areas to perform because it's never going to see the sun, right? Areas that need structure, we put in structure. Areas that need performance, we did. And so you can see here on the right how transparent it is. We were able to remove a lot of material from there. On the left, they have longer flaps, and in this video you can see why. A lot of people were going to the site thinking it's like, oh, well, we're going to see this thing actually move. The thing that you have to keep in mind is it doesn't move when you're standing there because the temperature doesn't change like in 10 minutes. It's typically the same. Sometimes it does, and it will if the temperature changes. But basically, it changes over the course of the day, over the course of the year, that kind of stuff. And so you can see here when the shade goes over, all the pieces start to shut. This led to assembly strategies too. So that same project, I told you we had 14,000 pieces. You know, no one has ever built something like this before, neither have we. We got all our pieces laser cut, they were delivered, then we had to sort them. We tried to sort them here, you can see, then we went to lunch, came back from lunch, and everything was all messed up. We didn't even think of how the sun was going to affect making these things. So it was a bit of a headache trying to keep track of 14,000 pieces for a project. So then after that, I thought, you know, gosh, you know, you can see all the different pieces have a lot of parts to it. I thought, it's like, wow, it would be great if we can do a project with just one piece, right? That we wouldn't have to sit there and, mark everything and catalog it. So here's the material, typically how it comes. The bimetal comes in a roll of material. And so the idea that I was like, okay, well, if there's this roll, we're going to cut it in such a way you see in this picture. Through all these ideas of how to cut these things, and then this one had a type of framework that can slide together so that this could be flexible in different areas. So the same system could look very differently depending on how tight it was made. In other areas, we wanted, again, longer flaps. You can see in the sketch at the top left there in pencil that as the thing goes around, every single knob was different going this way. But at least we didn't have to catalog where it went. It would just automatically wind together in the right place. So you can see that here. And then number 9 is where it was idiosyncratic. We then all realized that, well, we had this great idea of structure changing. And so that is the point where the structure changed, what you can start to see here. We became a little more ambitious because we needed structure. And instead of putting just an internal structure in there, we decided we wanted to make a structure that would go in and out. So it would be an endo-exo structure, right? And you can see how we go through it here, the shape of the structure that's starting to emerge, the different iterations that we go through as we start to develop that structure. And finally, you can see the 2 pieces here on the top. You can see the structure all connected together, as well as the plastic that's all in a coil. You can see below that we would actually build it in a long tube before we wound it back. But again, it was made in such a way that it was so flexible that from that paper cutout that I showed you earlier, that we're able to move it in very different ways. So you can see it here. The inside actually has a heating element on the inside so that all the long flaps on the inside would actually then curl towards the middle of this donut hole as it was heating up. We work on structural surface too. So we have structural surface where we use a much thicker bimetal. It's very difficult to bend with your hands and with, it just requires a huge amount of force. But when you heat it up, it just curls really nicely, right? So it's like, we're going to use this curl, we're going to heat it up to about 300, 350 degrees in an oven during construction, so that when it cools to room temperature, it then wants to flatten back up again, but we constrict it into what's called a pre-stressed form. It's just like a bow and arrow that's extremely, extremely strong. You can see it's a one-hand, one-person operation. You just need tools, right? There's no tools needed again. Very simple construction. Here on the left, you can see we had one person in the middle. We had another person coming and bringing the hot pieces from the oven. In the back, you see that kind of white oven here, right here. Labs. You can see that the outside colored pieces are aluminum. We want to differentiate that very carefully. On the inside, the silver pieces are the bimetal, right? And so you can see it being put together. Some people ask us where we get our funding to do the projects, and I tell you, we're very creative with where we get the funding because no one's out there just handing the money out. In this case, there was an aluminum fabricator who was willing to do a lot of this stuff as long as we featured the aluminum. So we had to come up with a way to feature that aluminum, and therefore we put the bimetal on the inside rather than the outside so that we can show it. The funny thing about this is, we build a lot of our own things. You can see that we were there in our time-lapse video. And at the end, we think of everything. But at the end, the person that was in the middle was stuck there because we didn't know how to get him out. So it was a 200-pound thing that we built, and we just looked at him just going, okay, now we got to get you out. Everybody went home in that facility. Luckily, we just used the pulleys and was able to get him out. Could have been a big OSHA problem, but we did it. The idea is that it was actually the bottom tier of a 5-tier tower that we're going to build. And so we're in the process of putting that all together and testing it for structure. We work with a big international engineering company called Arab Engineering to figure out the structure itself. It was surprisingly complex that it actually crashed their computers to figure out. Still don't know how much it can hold, but they're guessing something like 4 tons. Other biology things. So again, I'm trying to take the same idea. The column is a very vertical one-way system, right? Or we could say two-way, right? Vertical system, the way it was designed. In this one, we were trying to think about a surface. So in architecture, everything we do is big surfaces, right? You look at the surfaces everywhere. We have to enclose. So how do we translate this into a surface? And so this project actually did that. It's trying to look at these surfaces using the bimetal as a way to push the structure out, to add more strength to it. So in this case, we make a lot of these mini prototypes or ideas putting together. We start, and I kind of put these relative to the scale that we build them. The paper ones are probably about 6 inch. Then we move to 2 feet. Then we move to 3 feet, which are these silver ones in the bottom, before we get to actually building the final thing, which is a 9-foot diameter piece. You can see that again here, the silver parts are the bimetal. They're the ones that actually want to flatten out, but we're constricting them here, and the colored pieces are aluminum. There are no fasteners in here, and the petals that are actually hugging together are designed to hook onto each other to not explode, right? This entire thing wants to explode. It's funny, I say this too because a lot of people think, oh, where'd you get your aesthetic? And it looks just so, like a plant or a tree or so feminine. And I go, we're just designing it to perform. And it just turns out to look like this in the end. You can see us putting it together again. It's a fairly quick construction. This took us over 2 days to put together. It's now at the South Coast Botanical Garden. But the interesting thing is the thing becomes very, very floppy until that last piece goes in there. Once that last piece goes in there, and all of a sudden it stiffens up into the sphere that you can just roll around. So here it is. There's different renditions of it. We keep changing it because it's a botanical garden. It's kind of nice to continually test things on it. We do self-assembly too, right? So you saw before 1 hand, 1 person construction. Now this is 0 people construction. We started doing this with very small things here, just using heat, shapes, geometry again to do that so that they can go together. They can go into position itself. It's funny, it's these little things that, we don't spend that much time on, but NASA and those kind of organizations are coming to us to try to develop because they can't take a crew of construction or contractors up to the moon or to Mars and are trying to figure out ways that they can self-assemble. This is another project that actually is a wheel. Currently, it's a wheel that's going to be for a flat pack vehicle. It's a toy vehicle. But the idea is that you can go down out to the desert. First, we were trying to use those solar turbines that you saw that I was saying to cool people as the way to propel this thing. And was happy to hear that DARPA offers a lot of money to make self-driving vehicles. It didn't say at first that it had to take humans, so we'll see where we get with that. Window shading. This is something, and it gets back to the project that we did here. Let me back up for a second. A lot of these projects are in beginning idea stages, right? They seem like they're for architecture, a lot of them, if they're not for application, if they're not put on buildings, to me, it's like, then where are we going to go with architecture if we can't get these products out there? So this product actually is one that actually is now commercially available. Basically is looking again at that energy use. Here's our problem in architecture. Buildings use 40% of all energy. If you compare that to transportation, which is 28%, industry, which is like factories and stuff, which is 32%, that's a lot, right? When you think about buildings. So as an architect, I'm sitting there thinking, it's like, well, why aren't we doing more about buildings? Why aren't we all talking about saving energy in buildings? You look how it breaks down too. HVAC is heating, ventilation, air conditioning in a building. The most goes towards that, right? Even as we sit here, we're actually nice and cool. But it's right now, air conditioning is going on in every empty room in the building probably all night, right? Lighting makes up 25%. We all need the lighting, but they're trying to find ways to reduce the need for lighting. And equipment, which is more like computers and that kind of stuff, takes up a lot of energy too. So my idea is like, okay, I can't deal with all of these things, but if we can take that HVAC or the air conditioning cost down even 1%, that's a big deal, right? In addition, in our cities, we have the heat island effect. Many of you probably heard about this. A lot of it is due to all the hard surfaces in a city, right? It doesn't have enough trees, enough reason. What happens is the sun comes, is absorbed into these hot surfaces, and at nighttime, it radiates that heat. Out in the country, right, the hot air comes during the daytime, but at nighttime it's cooled from the soils, from the trees, from all these different things. And so our cities are doing a lot of harm to this problem. In addition, what I try to show here that people don't realize is air conditioning is specifically adding to that problem. In order for any air conditioning to happen, any air conditioning in this building that we don't see because it's in a central mechanical system, but any kind of window air conditioning system that you see in residential places, it has to give up hot air to cool the interior. If you go outside and put your hand out there, it is spitting out hot air, right? So if you think about all this, as the cities are getting hotter and hotter, people are using air conditioning more and more, it's contributing to this problem of rising temperatures. On top of that, you just look, and even in the US alone, 12% of all energy is used just for air conditioning. All energy, right? This is not, 12% may not seem like a big number overall, but if you think it's just for air conditioning, and that's the calculation for everything, then it's really, really abysmal. So how do we deal with this problem? Here's the typical problem. Here's the windows that everybody likes, right? Floor to ceiling, 360-degree view everywhere. But the reality is, even in that image, the difference between the shaded areas and the sunny area is different, right? You prefer even still to stand in that shady area to stay cool. There's reasons for that. So you see on the right, we have a double glazed window with no coatings. I'll give you a little education on how these windows work. No coatings. The coatings are the tinting that keeps it cool, right? It's glow-e coating that you see on all these buildings that make them dark. So they're actually quite good chemically, and they're pretty inexpensive, but they're turning out to be not good for human wellness. So this low-E coating you can see here, the reality is if you saw without the coating how clear your view would be, here's the difference. It's like wearing dark sunglasses all day long, right? But you just don't know it because you walk into these buildings and they're already coated. We have electrochromic glass, what you see on the right, and that's the very cool dynamic glass where you turn the switch on and electricity goes through and all of a sudden it's opaque. It's extremely expensive to install. There's a huge amount of wiring. Something goes wrong, you got to rip open all the walls, right? It's a problem. And on top of that, there's some color tone to it that you can't get rid of. Blinds, as well as shades. They seem to do well, right? Everyone thinks, oh, the sun's coming in, I got to put the shades down. It actually helps with glare. It does not help because the heat already entered the building. The air conditioning still has to condition the same air. So it's not saving energy. It might be keeping you from being hot because you're just standing in that solar radiation, but the room is just as hot. It doesn't matter. So the product that I designed actually sits inside the double glazed window in between. It's these little pieces of thermal bimetal that are cut that basically flip when the sun comes across to shade the interior. So you can see on the right here, as they flip before and after, it actually does not change your view. It does not constrict your view. It just flips over to add shade to it. So it's kind of a simple project, uses zero energy. You can see it up close here as they're moving, as the sun comes across, they flip over. You're sitting here on the interior, the exterior is now being blocked by these pieces. And again, keep in mind that these are between two pieces of glass, so you cannot touch them. We've installed it in different places around Los Angeles. This is actually in Hawthorne, California. There is some obstruction of view, obviously, but the beauty of it is by having them in there, we can get rid of all coatings. So the glass itself is absolutely clear, and you can actually see through the clear glass into buildings, unlike those high-rise buildings that I showed in the beginning. And this was a project that we had on your campus here. It's near the engineering buildings. I don't know, did anyone see this at all? Some of you saw it, right? We just removed it a few months ago. It was here during COVID and stayed up for almost 2.5 years, maybe. What we did at first, and the reason why we had it out here, is sponsored by the Art Museum. Half of it, we started out with clear glass. And so we had all these testing units inside to test how effective these units were. We were able to find that it saved about 30% of air conditioning, the difference between having a clear glass and this invert system. You can see that, again, we work with artists so that we can use the artwork that's pixelated that runs through it, which is incomparable to probably anything you've seen before, right, through glass. We've gotten a lot of recognition, one from the Cooper Hewitt National Award, a couple years ago, and then last year we got the Time Magazine Best Invention Award. So I'm going to end up with these two projects on public health because it's stuff that I'm working on now, and it's kind of right in the forefront of what I'm thinking about. In architecture, we have not only the surface, the concrete surface that are contributing to heat island effect, we have a lot of building surface, right, that's really untapped. And so my proposal is, why can't we use all of these surfaces for infrastructure? Why can't we use this all for the public good somehow? And my personal interest is in the area of public health, but it could be for a lot of other things too. You're starting to see it in individual projects, but I actually want to promote it so that it's a requirement of all future buildings to do this. Instead of being a pretty face for that building, why can't this be a wall of the city and perform for the city? So one of the projects that I'm working on is trying to make smog-eating panels, right? In these cities, a lot of people are starting to have a high level of lung disease, especially in the underserved populations who are sitting there at buses all the time. So there's cities across the world that don't have access to a lot of electricity again, that don't have access to high-tech things that are going to clear up this air. So why can't we use architectural surface to start to do this? The idea is to try to use, again, physics of air movement. You can see on the left, this one actually is showing what's called the chimney effect, because hot air rises. So why can't we use this hot air rising? And why can't we make these things so that they'll, again, run air through it to filter? Our intention is to initially build a bus shelter, because people waiting for buses are the ones who are sitting there the longest, breathing the worst amount of air, right? In particulate matter as well as noxious gases. And so the idea is to redesign the type of bus shelters so that they're ultimately the freshest air pockets in the city and give those fresh air pockets to those waiting. You can see here we're working through, again, a lot of technology, simulation modeling, working with aerospace engineers to kind of get air movement across the surface, giving 3D printing in clear glass so that we can run smoke through it to see how it operates. And the idea is to then come up with these systems of arrays that can then start to be developed for architectural application. There's a lot more to this. There's a lot of detail I won't go into, but we have two different models that we're working on. One is using prevailing winds, so that you can see here the openings are actually rotating to how winds move inside an urban canyon and send them through these tubes or facades to filter. And the other one is the chimney effect, right? And trying to use that heat rising, and so that as it comes to the surface of a building, it looks like a little bit like a cheese grater right now, but how we can get air to move up and out and use these facades to do something for the public. Keep in mind that no developer or owner in their right mind is going to want to spend extra money on a building and try to do it for the public. Why do that, right? And so we have public policy people on our team to really think about how we can change requirements in cities, how we can think forward in using these surfaces. And maybe it's going to take us 100 years to get there for the public good. The last project, which is also about public health, actually uses this idea of robotics. I put this in here because in my practice, when interns come, one of the first things they do is make these little critters. And first it was just an exercise that they would just play around with so that they can start to understand the material. And they would do this for the first 2 weeks. And they'd make, the success is finally getting something to actually move and propel. And we'd have these little races. They'd be the slowest races in the world because you can see this thing can hardly go anywhere. But it was funny because when we show this to people, a lot of people smile and they laugh and they think it's so cute, and there's a certain amount of emotional value connected to it. And I thought at first, it's like, well, I don't know. It's like, how is it going to, influence architecture? And I always put it aside, and we had this pile of these little critters, never thinking that it would amount to anything. But then I started thinking about mental health and how architecture and these facades are so big, and you're walking and you're looking at them, how they can actually contribute to mental health. And if we can try to get these ideas from these critters and translate them to buildings so that we have more connection to the building, so that we start to enjoy looking at buildings and we start to love them. We look specifically for our friend on this building and these imperfections and these ineffective things that may on one hand be performative for the building, but on the other hand actually start to contribute to wellness. Because the idea is, if we can make one person smile, if we can make 10, 100, 1,000 people smile a day, we can actually improve the mental health of a city, even by a small increment. So how do we do that? How do we go about that? And this is what we're now starting to get funding on this project. Once we started looking at, why don't we just make the building smile at you? You know what I mean? How about that? And find different ways to do that. But it turns out that, it's not connecting with people enough for them to smile at it. They just kind of, more are inspired. We're finding that it's the movements that are coming out on the surfaces that people are, either surprised at or, alarmed at or react to. So it's that movement system that becomes really important. And the funny thing that we're starting to learn is that they're interested and they respond to the imperfections in the surface as opposed to the perfection, right? And so much of our world in architecture is about engineering and getting to that place of it needs to work perfectly, all aligned, at the same time, no mistakes, efficiency is the goal. The goal for this project is actually inefficiency, and is trying to look for those moments that people, are pointing out where it's not working and either laugh at or react to it. So on that note, I end with this slide, which is The Flayed Man by Richard Barnes, which really speaks to me a lot because it's a skinless person, right, who is supposedly weirdly positioned in a way to be leading all these skeletal elements to absolutely nowhere, right? So where are we going with all this? And thank you very much for coming, and I hope that gives you an idea of my work. Yeah.